Hello, everyone. My name is Brett Daly, and welcome to today's Pro Skills webinar on Induction Heating Fundamentals from Ambrell Corporation. Dr. Girish Dahake, Ambrell's Senior Vice President, Global Applications, will be presenting today. Girish has over 25 years of induction experience and leads a worldwide team of induction application experts. He holds a PhD in Mechanical and Aerospace Engineering from the University of Rochester. Today's webinar will last approximately 1 hour. Please enter any questions you may have into the chat or Q&A windows on your screen, and they will be addressed during a 30-minute Q&A session that will follow the presentation. When you leave the webinar, a survey will pop up, and we'd appreciate your feedback. Thank you for joining us today, and now I'm going to turn it over to Dr. Girish Dahake.
Good morning to everyone who is attending this webinar from the US, and good afternoon to all of our European friends attending from there. And good evening to the people who may be joining us from Asia today. So today's webinar is going to highlight some of the basics of induction heating. We are going to first start by comparing different sources of heat that an engineer may be presented with when they are looking at a heating solution for their manufacturing process. We are obviously talking a lot, or will be discussing a lot, as to why induction. And we are going to go through some required and necessary components of an induction system to boot. So when one thinks of heat, what is the usual thing that comes to mind? Usually flame heat is probably the oldest and one of the easiest to incorporate in a heating process. However, once you start a flame heating process, you quickly realize the limitations and the challenges associated with this kind of a heating process. Flame heat is really inexpensive to set up, but the long-term reliability and the repeatability of a flame setup leaves very much to be desired. We actually had a couple funny instances where there was a company where they got one induction system and they had 4 or 5 flame setups, and heard through the grapevine that the workers started coming into work earlier every day. And over time, they figured out that nobody really wanted to work on that flame setup anymore, and they all wanted to work on the induction setup. So whoever came in first got to choose what setup they wanted to run. And induction started to be the setup of choice for all these people. That was a funny story. It took this company almost 3 months to figure out why there was a race for people to come in the morning. Um, Things like that, because of the associated disadvantages of a flame type setup. What else can be done? You can actually take the flame heat or any resistance form of heat and control it in a large box as an oven or a furnace. Now when you have to heat a part, you open up the oven, put the part inside the oven, and the entire part comes up to temperature. It does offer a very good temperature control because you can control the mass of the furnace or the oven to control the final temperature on the part. But one of the disadvantages of this type of a process is that the installation is typically pretty big because you're trying to reserve or just build a lot of heat capacity inside the oven or a furnace. The startup time and the shutdown time of these furnaces is really long. So a lot of times, even if the parts may not be running through the process, the oven or the furnace still is going because of the problems associated with the startup and shutdowns. Another form of heating is called as resistance heating that is available. This type of heating relies on the electrical current being fed directly through the part that you are trying to heat. It is extremely efficient. Resistance heating in a lot of cases approaches 99% plus type efficiencies. However, with this kind of a process, there are some repeatability and reliability concerns because you have to contact the part and introduce the current and remove the current from the part every heat cycle. This causes some sparking issues, but it's very inexpensive. And a common example is like a toaster oven that we use when we have to toast our bread in the morning. Once you press the switch, the filaments in the toaster oven come up to temperature instantly. And that's a quick example of a resistance type heat. There are some upcoming technologies that are there, like lasers, which are able to deliver pinpoint accuracy in the heat that they produce. Their high power density is extremely high, but the heat zone that a laser produces is very, very small. And lasers are associated with some limitations on the surface emissivity and the shininess to be able to deliver the heat. However, I believe strongly that laser technology is going to grow, but it is still not as cost competitive in bulk heating when compared to this next method that I'm going to talk about, which is induction heating. Induction heating can just be characterized as industrial heating. When you have to heat a part, no matter what the application is, induction is a good candidate unless there are some limitations to using induction. In our company, my toughest job is to actually say no to an induction process or no to a heating process being induction, because the heating is so precise, heating can be controlled, it finds a lot of use in the industry. So when we have to decline a project as an induction project, it actually hurts because the entire chain is looking to sell induction. So why would anybody want to look at induction? Induction heating is highly selective in its heating. It's one of the big advantages of induction. And the advantage comes from the fact that you're heating a very small portion of the metal, which means that once the heating cycle is completed, to cool the metal, you actually are going to have to cool less of the metal. If the same part was put in a furnace or an oven, then the entire part has to heat. And after the heat cycle, the entire part has to cool. Therefore, the energy consumption with induction, if your application requires selective heating, is very, very high. So the efficiency is extremely high. Induction is also extremely repeatable. One of the repeatability examples is a dental tool. When you're sitting in a dental chair and the uh, dental surgeon is working on your teeth, you never think if the mirror or the pick is going to come off the plastic handle. If that kind of thought crosses our mind, it would be even more difficult to sit in that dental chair and go through the procedure. This is the kind of repeatability and confidence induction process builds in a manufacturing process. Once set up correctly, it will repeat itself cycle after cycle to produce good uh, parts. There are, however, some other applications like the medical industry applications, like aerospace applications, where given the repeatability of induction, it's still not enough. People want another form of validation for the process. Induction offers the advantage of supplying temperature control on the process as well. So you can get pinpoint temperature control, you can record the temperature and validate that the induction heating power supply was uh, delivering the right amount of heat as was designed. Another big advantage of induction is that the heating is non-contact. What do I mean by that? In a furnace or in an oven, the heating of the part is through radiant energy or convection energy. In a flame type process, the hot gases emanating from the gas torch have to hit the part and transfer the heat. So in induction, none of this transfer medium is required. The energy transfer is through magnetic field and magnetic flux and doesn't have to have any medium for that transfer, similar to the energy that we receive from the sun. Since no transfer medium is required, the induction energy can be transmitted through non-conductive materials. Picture on the bottom right shows the filament inside a tube light being heated so as to release mercury off a capsule. It's an old application, but it was one of the only ways you could heat that mercury capsule with uh, using this technique of non-contact heat generation. Induction heating process is also extremely clean. Because there are no byproducts produced by this process, the process finds its use in clean room type environments, in applications that require extreme cleanliness. Medical industry, fiberglass industry, or optical fiber industry are common examples where induction is routinely used. We did talk a little bit about the energy efficiency of induction when compared to other forms of heating. Imagine an example where a part is being put into a furnace, but only a small section of the part had to be heated to affect the thermal process. With induction, you can just calculate or determine the amount of metal that is going to be heated. However, when compared with an oven or a furnace, not only do you end up heating the entire part, but in a lot of cases, you also end up heating the fixture or the holding device that has to grab the part in the right location for the process to work. So you are forced to deliver heat into the entire part as well as the fixture every cycle. So energy efficiency comparison is then not fair because induction just seems to be much more efficient than these types of processes. Another major advantage of induction heating is that in the last maybe 10, 15 years, the advancements in semiconductor devices has allowed the devices to be much smaller, but much faster. Memory is now almost free. So this type of technological change has led to the induction power supplies being much smaller, much faster, much more reliable as well. Induction heating used to be, for the most part, a batch type process in a lot of companies because the induction machines were big, they were dangerous, so there were some safety concerns around that. So it was prudent to have induction heating cells just dedicated to induction. So there was a lot of batching requirements that were commonplace in the industry where you had to collect a lot of parts, bring it to the induction setup, and then run it. With the smaller power supplies, now it is possible to place the induction heating machine in the manufacturing cell itself so as to get the most benefit from lean manufacturing principles. So what all can be done with induction? The number of applications that induction can be used for are so numerous that it would be impractical for us to talk about all of them during a webinar type time period. However, this is a brief list of some of the more common applications that come through. There are some that are pretty unique. There are some that are pretty mundane. But overall, induction is a good solution unless there are some overarching circumstances that induction cannot be used. When you look at any of these devices, look at planes, trains, automobiles, whatever, the basic building block for all these devices is the metal. And metal goes through a lot of transformation from the basic ore, where it's melted, to the final product when it's used inside these devices. The first process, and in each of these transformation processes, heating is a very important uh, function. Taking the ore from the ground and melting it to form the basic raw metal is a heat intensive process. This is done in big furnaces and big melters, and they are technically called as smelting units. A lot of these things are a combination of induction and some other form of heating, whether it's a plasma arc or some other form of heating. Induction is used though to melt these types of metals as well. Once you get the basic raw material or the raw metal, you have to decide where the metal is going to be used. For example, a camshaft in an automobile is going to require a different mechanical property than, let's say, for example, the skin of the car, which is made out of a different metal. So different metal compositions have to be made. And so the metal that was just produced is then remelted, and different elements are added to it to make different alloys. These alloys impart the metal with its unique specific mechanical property that allows it to be used for that process. Once you have the actual alloy, then the same metal is heated once again in a process called as forging. This is where the metal is heated to just below the melting temperature, and the shape of the metal part is formed, whether it's a bolt or a crankshaft or whatever the shape may be. That's how these shapes are formed by the process of forging. In this process, like I said, you're heating the part not to the melting temperature, but below the melting temperature to formulate the shape. Forging type environments or applications are relying on good heat to the center of the part. You want the entire part, including the core, to heat to the same temperature. That is why you will see in a lot of induction processes, multiple parts are heated at one time so as to allow for the time to soak in to the center of the part. One of my favorite analogies is that you cannot turn the oven temperature higher come Thanksgiving time and cook your turkey faster. You can't say, okay, give me twice the temperature and reduce the time by half, because it takes a lot of time for the heat to penetrate from the outside surface to the center. That same analogy on a much faster scale happens in the heating of metals as well. A piece of metal takes a certain specific time to take the heat from the outside surface to the center of the bar. Once you get the shape, uh, and again, sticking to our example of a crankshaft or a camshaft, there is another heating method that is employed on that same piece of metal, and that is called as heat treating or hardening. In this type of a heating process, locally the metal composition is varied so as to make it more wear resistant or much tougher, so that when in operation, it doesn't wear that quickly. Heat treating also is prevalent in a lot of day-to-day devices or tools that we use. Hammers, chisels, knives, they all go through a process called as tempering, where they're heated to a low temperature so that the part is not extremely hard and not brittle and can be used in the application that it's intended for. There are some more heating processes in the manufacturing industry, like curing. Curing of different coatings, curing of different additives on the metal surface is hastened by the addition of heat. The top two pictures in this slide show a brake rotor being heated, where anti-rust coating is applied to the brake rotor, so that with these new fancy cars that we have with very thin spokes, you don't see a rusted rotor when you look at a wheel. And the coating actually preserves the metal surface from being rusted. Brazing is another common application for induction. The brazing process involves joining of two similar or dissimilar metals by the addition of a filler metal. The filler metal is usually a mixture of a couple of metals. This mixture melts at a much lower temperature and is able to make a joint that is as strong, if not stronger, than the parent metal. So it almost works like magic. But brazing applications are there also in the industry because you can use two simpler looking parts, manufacture two simple looking parts, and then join them together to make a part that is extremely complex in shape. Brazing processes are all over. Flanges are brazed routinely on shafts. You have brazing in a lot of plumbing industry. The process that is analogous to brazing is called as soldering. In the soldering process, much lower temperatures are required because the filler metal used is typically a combination of tin with silver or tin with lead. Tin lead solder we are all familiar with because that's what is used in our indoor plumbing. So, however, with the move away from lead in the solder process, now tin silver solder process is gaining much more momentum. Same process, same typical setup, but a little higher temperature because of the silver being involved in that solder. Soldering is used in circuit boards, the soldering is used in speakers, soldering is commonly used in a lot of sensors. Small parts, low temperature, so typically lower power consumption in the soldering processes. The unique property that allows a soldering process to work is called as a eutectic combination. Solders are typically eutectics of two or more metals, and when they are liquid, they are actually able to fill the joints and the voids, but their melting temperature is much lower than the melt temperature of each of the components that make that mixture. That's why brazing and soldering are its own science. And there are a lot of different eutectics available. There are a lot of different uh, combinations available that will melt at different parts. This allows a manufacturer, for example, to have a high temperature braze and a low temperature braze occur on the same part. To run the process, you first run the high temperature braze alloy. Then to join another part to that same piece, you make the joint with a lower temperature brazing alloy, which does not melt the high temperature joint that you have just made, and allows you to make complex parts. Another very simple application for induction is called as shrink fitting. Shrink fitting is utilized in the industry because it eliminates the use of extra hardware to join parts together. It relies on just the properties of the metal to bind together two pieces. The way it's done is you heat the outer piece of the metal. Because of the heat being applied to it, the metal expands. Once you put a cold part inside the expanded bore, as the part cools down, it actually shrinks and grabs on to the part that was put in. This type of a shrink process is historically been used in a lot of different industries. We all know of bearings, even railroad wheels are made with a shrink process where just the outer surface of the railroad wheel is made out of steel. Everything else is made out of a lighter material like aluminum. Whenever we open up a medicine bottle or we are opening up a juice box, a lot of times we find that there's an aluminum foil seal that we have to get past before we can get to the product. The aluminum foil seal is there for a couple different purposes. One is that it acts as a moisture barrier and preserves the quality of the product inside the package. The other is aluminum, being a metal, can be heated with induction to make the seal on the package. Aluminum foil seals are typically done in a fraction of a second, and they don't affect the product that is being put inside, but can be heated locally to form the seal. So next time you open up a medicine bottle and you're trying to peel off the aluminum foil, just look at it carefully. You will see that the heat affected zone is only limited on the outer perimeter. That is what induction is able to provide. In a lot of turbine blade manufacturing, induction heating is used to repair the blades after they have been used in a turbine for a certain number of hours. Typically, the tips of turbine blades, because of the wear that they experience, will either chip or break. And it's not practical to throw the turbine blade away just because of a chipped top, because these blades are extremely expensive. Induction is used routinely in combination with laser heating to rebuild the turbine tips so that the turbine blade can be put into service again. A lot of non-metals are heated with induction as well by incorporating a susceptor type material, which basically acts as an intermediary between the induction coil and the part that is the non-metal. Semiconductor industry routinely uses graphite as that susceptor material. You can heat the graphite to high temperatures. It maintains its mechanical shape over a wide range of temperatures. So it's easy to transfer the heat from the graphite to any semiconductor. And then there are a lot of odd shape heating applications where it's impractical to form a coil around the part as a rigid coil. So there are some flexible induction heating coils that are produced that can be wound on the part and unwound from the part after the heating process is complete. Metal to plastic bonding is another very common application for induction. A fun tidbit is that when the Titanic sank in the 40s, there were very few plastic parts on that whole ship. Picture an ocean liner of the day today, any cruise ship or anything. It would be impractical to imagine that plastic would not be everywhere in the ship because it's lightweight, It can be coated with different coatings to make it look pretty. So plastics are finding a lot more use in the industry, not only because it's lightweight, but it's also coming up with a lot of strength now. Plastics are, if not as strong as metals, but they're approaching the strength of the metals. However, when you have a plastic body, you still have to anchor it to the rest of the machine or the assembly. Metal inserts are still preferred to be the anchor devices. Metal inserts are therefore heated with induction and then pushed into the plastic bodies to make the joint. There are some atypical applications of induction, like in the shell annealing applications, where brass ammunition shells are heated so that the metal can be softened to be shaped into the shape of a shell. How many of you have heard that a chain is only as strong as the weakest link? Well, if we can make or produce a chain with every link being processed through the same type of heating process, then every link will have the same strength and it makes for a better final product. Induction is used in a lot of food industry applications. Manufacturing of cookies that go inside of chocolates is made or is done with induction heating, very common. Induction is also used to burn off varnish or enamels of motors so that electrical connections can be made to these wires. Induction heating is also used in the manufacturing of engine blocks. I don't know how many of you know, but aluminum is actually injection molded around preheated steel liners to actually cast an engine block. The steel liners are where the piston rides inside, and the steel liners are there because they offer a much better wear surface for the pistons than the much lighter and weaker aluminum that is the rest of the body of the engine block. And depending on what model is being used, you can heat 4 or 6 or 8 steel liners at one time for this type of a manufacturing process. As you can see, the induction coil has to conform to the type of engine that is being produced. A lot of rivet heating is done with induction heating. Rivets hold plates together. You know, it's a commonplace to have rivets being produced on a mass scale, and you want a local crumple zone on the rivet. Induction is able to offer that localized heating on the metal rivet so that when put into action, it actually crumples and gives at just the right spot. So what's this induction heating setup, does one induction heating setup comprise of? Because we've seen a lot of different applications. We know that it has a lot better efficiency and a lot of advantages in a manufacturing process. So what is this beast? Induction heating setups are really simple setups. Going from left to right, the induction heating power supply is typically the major working component of the setup. The power supply takes AC line signal and water cooling and creates a high frequency signal. We haven't talked about the frequency yet, but we will in the next few slides. But the function of the power supply is to take the regular AC line signal that comes in our factories and then convert it to a high frequency signal. The output of a power supply is then fed into a tank circuit, which, as the name implies, acts as a storage device for energy. The stored energy is then discharged through the induction heating coil, which then heats the part. Let's talk a little bit about how does it heat the part. The basic principle of induction heating is the eddy current heating. Typically, when you have an electrical conductor carrying an alternating current, it produces a magnetic field around it. Once you place another piece of metal in the vicinity of that primary conductor, even though there is no external current being fed to it, because of its interaction with that magnetic field, it actually induces a current in itself. The induced current is a function of the distance from the primary, and it gets stronger obviously as it gets closer and closer to the primary. In induction heating, this primary conductor is wound in the form of a coil. The induction coil then has a magnetic field map that is shown here. As you can see, most of the magnetic field lines concentrate inside the induction heating coil because of just the geometry of the coil and just the way it's wound. This is beneficial because once you put a part inside the coil, it intersects all that magnetic field lines and magnetic flux and produces current in the metal part. One of the big uh, basics of induction is that it's only able to heat a metal part. That's why if this blue part on your screen was a non-metal, the magnetic field lines will just flow through it without creating any heat. The secondary part, which we are trying to heat, has to be metallic for us to be able to heat. If you have to heat a non-metal, you have to use a sacrificial piece of metal or graphite to transfer the heat from the induction coil to that metal and then transfer the energy from that metal to the non-metal. What's this frequency of operation that everybody keeps talking about? The line frequency that comes into our houses and factories can either be 50 hertz or 60 hertz, depending on which part of the world you are in. This means that the voltage and the current signal are cycling from a peak positive to a peak negative back to a peak positive in 1/60th of a second, or you get 60 of these cycles every second. Typical induction machines uh, run at kilohertz frequencies. So a typical 50 kilohertz induction heating machine will cycle that same current and electricity at 50,000 times a second. Now, what this does is it's similar to the phenomena we experience on a cold wintry day. When we rub our hands together faster for the same amount of force on the hands, we produce more heat. This is analogous to how higher frequency produces more heat into the metal part that we are interested in heating. The other big difference between induction heating and other forms of heating is that induction heating heats into the depth of the metal. And the depth to which induction heating can heat the metal is controlled by a couple different parameters. This depth is a function of the frequency of the operation of the induction heating machine, as well as the electrical resistivity and the magnetic permeability of the metal that is being heated. I don't expect you guys to remember this equation or to know of this equation, but I just want to give you a brief understanding that there's a lot of science behind the proper selection of the frequency and the power that an induction heating device is uh, recommended for. The frequency parameter can be used for a lot of different application processes. By changing that parameter, you can either heat to the center of the part or just heat on the outside surface of the part. This is utilized in different manufacturing processes. In some processes, it's advantageous to heat just the outside surface, like heat treating or hardening of metal surfaces. In some applications, it's actually advantageous to heat to the center of the part, like in a forging type process. So the right selection of frequency is important to be able to deliver the heat exactly where you need it. The choice of frequency can also be utilized or harnessed to our benefit in a manufacturing process. The video here shows that the picture on the right bottom, the large metal part is heating really easily in a large induction coil, but the smaller metal part, even though it's much smaller in size, it doesn't show any heat. So in a lot of processes, you can use that smaller piece of metal to act as a support for this larger piece of metal through the same coil. The induction heating coil, because of the choice of frequency, only heats the large metal but does not heat the small metal part. In magnetic materials, not only do you get the eddy current heating that we talked about, you also get a hysteresis form of heating, which is basically the heat produced because of the shift of the magnetic dipoles, because of the alternating magnetic field that is produced by the induction heating coil. So magnetic materials tend to heat much faster than non-magnetic materials of similar electrical resistivity. How does one determine how much power is needed to heat a particular part? A simple mass equation, thermal equation is used where if you know the rate of metal that is needed to be heated, the specific makeup of the metal, whether it's a steel, brass, aluminum, and the rise in temperature that is required, all are needed to determine how much energy is needed in the metal part to heat it to a certain temperature. Mind you, this is not the size of the power supply that is needed because you do have to account for conduction, convection, and radiation type losses from that uh, part being heated to basically get a good understanding of what is the total energy picture for this process. Once you know all that, you can determine easily what induction power supply is needed. A simple example we ran where we actually put some thermal insulation on a hot part, and we could see the benefits of the thermal insulation by getting hotter and hotter part without adding any additional heat into the metal part. There are some numerical simulations that are available nowadays that can guide you to actually start on a new induction heating process. These types of simulations are limited in their results, and they have to rely heavily on a whole set of boundary conditions that are present in the manufacturing environment. However, in a lot of applications, they can offer as a good guide to begin the design process. Let's spend a little bit of time on induction heating coils. Induction heating coils come in different shapes and sizes, and they can be made of different tube sizes as well. The rule of thumb as an induction heating design system designer is to use the simplest possible coil to give the best possible heat. on your part. Because the copper can be wound in multiples of different ways, you can use the same basic shape of an induction heating coil to generate heat in different sections of the same part. You can see this clearly from the 4 pictures shown here. Depending on how the copper turns are wound, you can get different heat patterns on the part. There are multiple position heating coils available as well. So a lot of times it is required to heat more than one part at a time. So you can use a coil that heats multiples of parts at the same time. In a lot of applications, the heat emanating from the part can be detrimental to the induction heating coil and lose a lot of energy through the copper coil of the induction heating system. Ceramic powder encapsulation is routinely used to shield the hot parts from the cold water-cooled coil. There are some other multiple position coils that can be used in a robotic cell type manufacturing process. The coils are built on an arc. This allows for the robot to not have to make additional movements, but it can then pick up parts from different stations as the parts get to temperature. Then there are some complex parts, but simple coil solutions to heat those parts. And this is where the common saying is that one test is worth 1,000 of experts' opinions. You know, a simple test can help guide you in the right direction in the selection of the appropriate coil for your heating process. Induction coils are numerous, like we said, in their shapes and sizes. Depending on the application requirements, the copper can be wound in a lot of different patterns. Let's spend a little bit of time on the cooling of the equipment. We spent a lot of time on the heating, but almost all of the induction heating coils are water cooled. The water cooling that runs through the induction heating system, as well as the induction heating coil, is working hard to keep the copper from heating up, and it maintains the efficiency of the system at an optimum level as well. If the water temperature through the system is varying, you might see process variability creep into your manufacturing process as well. The simplest cooling system that is available in the industry is a water to air type of cooling system. This type of system is relatively inexpensive, utilizes a fan and a radiator to basically cool the liquid or the water that's running through the system. The limitations are obviously the ambient air temperature and the duty cycle that the induction heating system is used with. Another form of a water cooler is a water to water type cooler, where a closed loop system is utilized to run a clean water loop through the induction setup, but the cooling capacity is derived from an external water source, like an overhead tower or an outside tank. This type of a cooling device is extremely efficient and can cool a lot of energy in a very small footprint. There is a third type of cooling device that is called as a water chiller. This type of device is obviously the Cadillac of the industry. because it houses a refrigeration unit on board. Doesn't require any external input. It can cool the water reservoir inside this unit to the temperature that is required for the induction heating process. Temperature measurement is another integral part of an induction heating setup. Typically, a visual thermal temperature measurement is not recommended. I've actually personally gone to a lot of factories where the operator will tell me that, yeah, that temperature on the part looks good, and I think that's what we are expecting in our process. It's good that the part runs, but it's not a scientific way of guaranteeing that your process is running in control. Thermocouples are one of the options available to measure the temperature of the part as it's heating. The temperature can be measured during the heat cycle or after the heat cycle is complete to validate that you reach the right temperature on the part. This is cumbersome though because you have to mechanically touch the part with the temperature probe to get the temperature. Optical pyrometers are a much better solution because these devices are able to measure the temperature on the part without touching the part. You only need a line of sight to the hot part to be able to measure the temperature. The optical devices can either be a single point uh, temperature readout or a surface map as shown in the bottom picture through a thermal camera. This type of camera is able to give you the entire part temperature at any instance. And as, like I said, advancements in semiconductor technology have benefited the induction heating power supplies, so have the advantages helped the temperature measurement industry as well. You can find more and more temperature measuring devices at costs that are really economical. So it's easy to incorporate temperature measurement in your heating process of today. Like we said, uh, even though induction heating is extremely repeatable, a lot of applications still require another form of validation for the process. One way to validate the process would be to do destructive tests on the parts, but that's not very productive because you cannot destructively test all parts. Another way is to record the output from the induction heating process, including the temperature on the part and any other parameter that may be important during the heat cycle. So a lot of software packages are now designed and available where you can record all the parameters of the process to validate that not only did you reach the right temperature on the part, but your induction heating power supply was also in control and delivered the same amount or same output cycle after cycle. This type of process is finding more and more use in statistical process control in industries. And as we gravitate more and more towards Six Sigma type manufacturing, where you want every part coming out of the line to be as repeatable as possible, uh, softwares like this are priceless. This is all I have for our webinar today. Thank you very much.
Thank you, Girish, for that informative presentation. If you haven't already entered questions into the chat or Q&A panels, please do so now. And with that, we'll kick off the question and answer session. Our first question is it possible to place a thermocouple inside of the induction field to measure temperature in real time?
The short answer to this question is yes. Uh, the thermocouple has to actually mechanically be mounted onto the part that you're trying to heat. If the thermocouple is not mechanically mounted to the part, then you will get a lot of interference from the induction heating field into the thermocouple. So what are the typical methods to mount a thermocouple onto a part? You can spot weld the thermocouple onto the part, or if you have to rely on just a press type thermocouple on the part, a lot of times the induction heating process is turned on and off repeatedly, and measurements are taken only when the induction heating system is off. Not very practical. So typically the best way to do is to anchor the thermocouple to the part. Also, the choice of the thermocouple wire diameter is extremely important. Smaller the wire diameter on the thermocouple, the less will be the interference that you will see through the induction heating setup. Another important factor in getting good readings of a thermocouple type induction setup is to have a good isolated temperature measuring device. A lot of the temperature measuring devices do not have good filtering in them to filter out the RF frequency that may be conducted from the thermocouple back to the device. So there are a couple different considerations to be had during the heating process when using thermocouples, but it's done routinely for long temperature cycle type processes. Material testing processes routinely use thermocouples in their setup.
Thank you, Girish. And our next question is, does an induction coil need to surround the part to be heated?
Very good question. Majority of the induction heating coils that you'll see are typically encircling the part. However, there are as many applications where the induction heating coil does not have to necessarily surround the part that is being heated. Obviously, it depends on what the metal characteristics are of the part. If the thermal gradients that are produced by a single-sided coil are not detrimental to the process, then surely a coil that does not surround the part would be beneficial in terms of handling and manufacturing setups. The round coil around the part obviously gives the most uniform heat pattern as expected. Thank you.
All right, and our next question is, does increasing the step to a higher step on the machine increase the frequency?
So this is seems to be a very subjective question to what the step is. If the step is an inductance step, then it does certainly change the frequency of the setup. However, a lot more information would be needed uh, in our factory to be able to determine what is the step mechanism that you are faced with. Thank you.
All right, and our next question is, would you please explain how condensation of water might affect the induction heating system?
So typically condensation occurs when you have extremely cold water running through the system on a warm, humid day. Similar to when you fill a glass with water from the refrigerator. Because the water temperature is cold, a lot of times you will see condensation build on the outside surface of the glass. This condensation can be extremely detrimental to induction heating setups because there's high currents, high voltages, high frequencies, all inside an induction heating setup. If the water condensation starts to form water droplets, then it may lead to arcs and sparks that may damage the electrical components inside your induction heating setup. Simple solution around it is to use a water to water type heat exchanger to uh, have a water loop that is temperature controlled above the dew point for your induction process.
All right, thank you, Girish. And I'm going to kind of combine two questions here, and because they're sort of related, and they are, one asked, what kind of testing or proof of concept does Ambrell offer? Then another asked, does Ambrell offer consultation of existing heating and recommendations for a new machine design?
So yeah, the short answer is yes to both questions. Uh, if the part can be tested, then not only does the company that is quoting the induction heating setup feel much more comfortable quoting the setup, the customer who is buying the induction heating setup benefits from knowing for a fact that the quoted induction setup is going to work well. It's typically not very time consuming to run a quick couple of tests to prove that the setup is a practical setup for induction. Ambrell labs are available, and depending on the nature of the part and the requirements of the heating cycle, we can evaluate how intensive the test setup will need to be. Thank you.
All right, thank you, Girish. And our next question refers to a slide during the presentation and asks, can you elaborate on why that small bar did not heat as much as a large bar? Is that mostly dependent upon frequency?
Excellent question and good catch. The small bar obviously was a different metal component than the large bar. The small bar did not heat at all because it was not magnetic, whereas the large bar was magnetic. However, even if the large bar was non-magnetic, it would heat readily in the induction heating setup that was shown. The small bar does not heat because of two things happening in tandem. One reason is that it the choice of frequency does not produce heat into that bar diameter. The second is that it's a small bar in a much larger induction heating coil, so the coupling on that bar was very low. So you got the benefit of that right frequency and very poor coupling to not heat that small bar at all in that induction heating coil. Thank you.
All right, and the next question is on the topic of operator safety. If I were to touch a winding with a metal tongue, what would happen to me?
So operator safety can never be underestimated. It is extremely important to be safe around induction heating setups because not knowing the make and the manufacturer of your induction heating setup, it's difficult for us to comment on it. However, when we are faced with any situation like this, where a metal part that an operator is holding may come in contact with the induction heating coil, the design of the induction heating coil has to change. You have to use insulators on the induction heating coil so that the metal tongue cannot come in direct contact with the copper of the induction heating coil. This is extremely important. And like I said, there are no compromises that can be made when it comes to operator safety. Thank you.
All right, and our next question asks, the software available uses a license. Where can we get that software? And I assume that's referring to eView, and we can have someone reach out to you about that after this session to help you. And the next question is there any advantage of square tubing versus round tubing?
Excellent question again. The square tubing allows the coil designer to flow a lot more water through the same cross section. So if you were to look at a half-inch round copper tube versus a half-inch square copper tube, you will find that the water flow through the square copper tube is much more because there is much larger bore in a half-inch square copper tube. Also, in a lot of rectangular copper tubes, the wall thickness of the copper can be quite large. This allows for better utilization of the induction energy that is being run through the copper coil. So a lot of low frequency setups and installations will typically require a thicker wall copper in the manufacturing of the coils. Thank you.
All right, thank you. And the next question asks, what type of thermocouple is recommended?
Typically, there is no formal recommendation on the type of thermocouple that should be used with induction. The most common that is seen in the industry is a type K thermocouple. It's available in lot of different varieties in terms of the diameter of the wires that are used in the manufacturing of these thermocouples. Ideally, the thermocouple should not have a metal sheath on it because the metal sheath interacts with the induction field, and it's better to have bare thermocouple wires with a ceramic or a silica insulation on it for use in an induction heating setup.
All right, and the next question is information available for induction heating copper tubing by OD in wall thickness? And if so, where?
Uh, Good question. This is a highly subjective discussion because it has to incorporate a lot of different parameters in the proper guidance and support to answer your question. We would recommend that you should consult one of induction heating experts to get the right solution because there is no readily available source that can account for all the boundary conditions that may be present in your process.
All right, and the next question ties in a little bit to an earlier question, and that is also, what would happen if a part were to come in contact with a winding? No, operator. Some of your images show the parts very close to the windings.
Excellent question. Typically, we do not want the metal part to come in contact with the copper windings of the coil. This is where, again, the design of the holding fixture comes into play. Given the tolerance of the holding fixture, you have to design the induction heating coil uh, with the appropriate clearances. If the holding fixture can move apart, let's say, for example, 1 or 2 millimeters, or let's say an 1/8 inch, then you have to make sure that the coil is at least an 1/8 inch away so that the part can never come in contact with the coil. If the requirement for a tight coil is based on the heating rates that are required, then a ceramic isolator would be preferred in between the gap between the part and the coil to isolate one from the other. This way, if the part were to lean to one side, it will come in contact with the ceramic insulator first before it can reach the copper windings.
All right, and the next question is, do I understand it correctly that the heat of the part inside of the coil can reduce the efficiency of the inductor?
Yes, if a part is radiating a lot of heat energy, the copper has water cooling running through it. So any heat that comes to the surface of the copper is just going to be sucked away. This reduces the overall efficiency of the induction heating setup. That is why if your process is heating the metal part to a very high temperature, and what I mean by high is greater than let's say 1200 to 1300 degrees Fahrenheit, which would be 600, 700 degrees centigrade, then it's certainly worth looking into what kind of heat loss is occurring through the copper. Simple solutions again, silica sleeve on the copper that is white in color, which reflects the radiant energy coming to the coil, or a ceramic isolator, a ceramic tube of some sort inside the coil to reflect the heat energy from coming to the copper. Thank you.
Thank you, Girish. And our next question is, I am using induction to heat a non-metallic material that contains metal powder to induce heating in the induction field. Can I use a thermocouple with this situation? I can attach thermocouples to the material, but it may not be in direct contact with the metal powder. Any ideas on how to measure temperature in the situation?
Very good question. So I just wanted to absorb all the details of the question to be able to recommend. Uh, the size of the metal particles is what is going to determine whether the diameter of the thermocouple wire or the size of the metal particles is larger. Because induction heating fields tend to heat based on the size of the metal particles. If the thermal mass of or if there is enough metal particles in the mixture, then you may be able to embed a thermocouple inside your part to be able to measure the temperature. However, like I said, a quick test will let you know if the temperature is a true temperature or a combination of the wire heat as well as the part heat. Ideally, if you are suspecting that the thermocouple wire may be heating, then I'm sure it is going to heat. In those kinds of situations, there are certain temperature measuring devices that are available that use fiber optic sensors that can work just as thermocouples to measure the temperature on your composite material. These types of fiber optic devices are typically lower temperature devices. They work maybe up to 500 degrees Fahrenheit type temperature ranges. So if you are having a problem with the thermocouple wire being heated with induction heating, and your application is a lower temperature heating application, then certainly you can resort to a fiber optic probe, which acts just like a thermocouple, and to measure the temperature during the heat cycle.
Thank you, Girish. And our next question is, how long does it take to heat a non-magnetic piece moving inside a pipe? Which variables are involved? Speed, temperature difference? What else is needed to calculate time to reach a desired temperature of moving of a moving non-magnetic piece?
Good question. Um, the if the metal piece is moving through a pipe, the heat energy transfer is typically being the heat is being transferred typically by either conduction or radiation. Depending on what temperature you want, then there are not too many variables that you can control on the induction heating setup. Because if I understand your question correctly, you're trying to heat a non-magnetic piece moving inside a metal pipe. But if the pipe itself is non-metallic, then the calculation is pretty simple and we can determine what length of coil is needed to get the right heat. Again, a little more information would be really required to comment to make sure that the answer is justifying your question. So pictures or drawings or some more write-up would be necessary to be able to answer correctly.
All right, thank you. And the next question is, are there considerations for the electromagnetic environment around the installed system in high power applications?
Yes, there are a lot of considerations to be taken around high power installations with electromagnetic radiations. There are testing agencies that are able to come to your factory and give you a map of high intensity versus low intensity locations for electromagnetic radiation control. This type of service is routinely employed by a lot of companies to ensure the safety of their operators.
All right, and our next question is, how is a typical induction stovetop different from what is described here? Could this presumably simple concept be used for low temperature industrial applications?
The technology used in the low temperature stove or stovetop devices versus what we presented here is exactly the same. There is no difference in the technology. It's the same basic operating principles that allow you to heat that pan to boil water or to do any cooking. The difference is that the induction stovetop is a very specific single purpose device. It will only heat a magnetic steel pan of a certain size. Because imagine if you were wearing a wristwatch or if you left your cell phone on there, it will want to heat that wristwatch or a cell phone. These devices have been designed to be smart enough to not be able to do that, but just be designed to heat that pan. With the industrial induction heating devices that we talked about today, they are much more flexible and are able to heat multiples of different metal parts without making much changes to the setup. Thank you.
All right, thank you very much. And our next question is, how may high volume induction heating be done on stainless steel tubing without creating a black appearance?
So the black appearance on stainless steel tubing is from the oxidation of the stainless steel tube in open air. So the oxygen from the air is creating oxides on the outer surface of the steel tube as it is being heated. The only way to prevent this oxidation would be to have an inert cover of nitrogen or argon on the steel tube during and after the heat process.
All right, thank you. And the next question is sort of along the same lines, is how can inert gases be used with induction brazing of carbon steel to reduce oxidation?
Good question. Same technique applies. There are a lot of induction applications that are done with a cover of nitrogen or argon, depending on the application. And this prevents the oxidation of the part and keeps or maintains the cleanliness on the metal part.
All right, and the next question is, are there any new innovations in preventing scale on steel parts during induction heating?
Uh, it follows the same line of thinking. Inert gases on the outside of the part will prevent the steel part from scaling. Also, the time that a part is at this elevated temperature will cause it to scale more or less. A lot of furnace applications require or tend to heat the metal part for minutes, if not hours. If you can do the same type of heat in a matter of seconds or a few minutes, then the amount of time available to create the scale is reduced. And that may be a simple uh, technique to reduce the scaling on the part. If the scaling is still prevalent, then employing an inert atmosphere on the outside surface would be required. If that also doesn't work, then you have to resort to a mechanical form of removal.
All right, and the next question is regarding arcing. The distance slash risk of arcing, how does that change with temperature and protective gas? Is argon worse than nitrogen?
So the arcing that happens is typically of a couple different types. You could have a turn to turn type arcing, or you could have a copper turn to the metal tar part type arcing. The former is very common with induction setups because induction coils haven't been designed right. If the arcing is because of the plasma generation, because of the gas that is involved, then you want a gas that has a higher arc potential to be used in your process. Unfortunately, I am not up to speed on my arc potentials for different gases at different vacuum pressures. I'm sure there is literature available on the internet that you could resort to get that information. Thank you.
All right, and our next question is about should they have one system with a 6-position coil or 2 systems with a 3-position coil each?
Either system works. A single system with a 6-position coil is able to heat parts as effectively as two systems with 3-position coils. Obviously, in the two-system scenario, you have some redundancy built in your manufacturing process, which allows you to be able to run at least one side of the manufacturing cell without compromising the entire cell. With the 6-system coil or 6-position coil system, if something were to not work, then your entire manufacturing process would come to a standstill. Thank you.
All right, and the next question asks about the absorption of the EMF by moderate conductors between the coil and the susceptor.
Unless the moderate conductor between the coil and the susceptor is metallic, we typically do not have uh, as much heating on that device because of the availability of different frequencies. You could use a smaller frequency which does not see these moderate conductors and goes through and heats the metal piece inside. you have to make sure that these moderate conductors are not continuous metal tubes. If they are continuous metal tubes, it does not matter what the metal makeup is. Any metal tube inside the induction heating coil will heat.
All right, thank you. And our next question is, what would be the best way to measure impedance through the composite materials?
I would have to take the fifth on this because I do not know this answer. Uh, I would need a little bit more information to be able to uh, get a good understanding of what the question really means. So feel free to send us an email or send your local induction expert an email with the question and some pictures or some drawings of what you are actually trying to accomplish from this measurement.
All right, our next question is, when would the coil need replacement? What type of maintenance or cleaning is recommended for coils?
A well-designed induction heating coil uh, does not need any replacement. The induction coil is just like the plumbing in your house. It just works without any issues as long as the water quality running through the induction heating coil is maintained. So if the water quality is not maintained, then you can certainly deteriorate the inside surface of the copper coil by either collecting deposits on the inside surface or by eroding the inside surface. Also, if you mechanically damage the coil, then obviously you will need a replacement coil.
Thank you, Girish. And our next question is, which direction on the face of the heat station or workhead does the magnetic field get out, left or right?
This one would also require a little more detailed information to be able to answer because the face of the heating station, I'm not quite clear as to what you mean by that, but we would love to have a little more information to be able to guide you correctly.
All right, thank you. And our next question is, what influence has the material aluminum have as a cooling shield around the coil?
So a metal shield around the induction heating coil made out of aluminum will absorb all the radiant magnetic field coming to an operator or to sensitive electronic devices. This type of aluminum shield is typically called as a Faraday shield. It can be made out of solid aluminum or perforated aluminum, very similar to the screen that you see on the front of microwaves. The perforations allow you to see inside, but it still does a good job in shielding the magnetic field that may be coming out. So similar principle applies in the induction heating setup.
All right, and our next question is, how well do flux concentrators actually work if they do?
Flux concentrators have a place in the induction heating setups. Flux concentrators obviously have a life associated with them. So depending on what kind of environment and what kind of induction setup you have, you may be able to benefit from the use of flux concentrators as long as the replacement cycle or the replacement cost of the flux concentrators is not too cumbersome.
All right, and the next question is, what is the main function of the cast material around the coil? Is it to isolate them electrically or thermally, or some other purpose?
I would say that you answered your own question. It is there to isolate both electrically and thermally. The white of the ceramic reflects all the radiation energy coming to the coil, and the ceramic nature protects against mechanical or electrical contact.
All right, and this next question, I think, builds on a little bit of an earlier question about induction cooktops, and it asks, why do induction cooktops not require water or air cooling?
So induction cooktops do require some form of cooling. They are typically air cooled. There is typically a fan that takes away the heat. But because they are designed specifically for heating that piece of magnetic metal pan, they are designed with that control in mind. The power that an induction cooktop is typically in the 1 to 2 kilowatt range. So it's not a lot of power that has to be dissipated, but like I said, they are designed specifically to be able to work in that environment.
All right, and our next question is, temperature measurement is one thing. How can that be integrated into a feedback loop with the induction system? I.e., we want to use induction to drive to a very specific temperature and then hold it for a time. Can that be integrated by Ambrell either by varying power, pulsing power, or possibly even changing frequency or something else?
Yeah, this kind of solution is a very common solution in the industry. Ambrell does provide a PID temperature controller that can take a thermocouple input and then regulate the output from the induction heating power supply to maintain the temperature over extended periods of time. So a very common solution, readily available, not a problem at all.
All right, and the next question asks, do you have any experience on an immersion solution to heat fluid?
I would have to say no because I'm not understanding the question clearly. So again, if you don't mind, you could send us some more information and we'll be able to then evaluate if it's something that's within our wheelhouse.
All right, and our next question is, tell me about the effectiveness of induction on flat rectangular shapes. Imagine a shape the size of a business card that is 2 millimeters thick.
Induction coils can be designed to heat that kind of surface. It depends what kind of temperature uniformity is desired. In some applications, if extreme thermal uniformity is desired, you would resort to using a susceptor material in between the induction coil and your metal plate. This serves as this serves two purposes. Not only does it give you better temperature uniformity, but also allows you to press down on the metal coupon so that it does not warp or bend on the susceptor material.
All right, thank you, Girish. And our next question is, to avoid heating a certain section of the part, is it possible through local shielding of the coil, or does it depend on just the geometry of the coil?
Uh, it is possible to locally shield the coil based on how the coil is constructed. So depending on if you're looking at shielding all around, like around the circumference and part of the circumference, then it's probably not as practical a solution. However, if along the length of the part, you want some areas to be hotter and some areas to be cooler, then that can be done with induction heating coil design. If you need around the circumference differential heat, then either a metallic shield or a contact shield would be required. You can also try and blow cold air on the part that you don't want to heat. But it all has to deal with what the actual application is and what are the details associated with that.
All right, thank you, Girish. Our next question is, what is the typical thickness of the copper tube used?
So ideally for typical applications, refrigeration tubing works pretty well for the manufacturing of the coils. This is determined by the frequency that the induction coil is going to be exposed to. Typically, when you're running in the 50 to 400 kilohertz range, then the commercially available copper tubing is a good solution. Uh, Wall thickness there is in 1/32 of an inch type parameter. So depending on what frequency you are using in your induction heating setup will determine what wall thickness is recommended. Thank you.
All right, thank you, Girish. And our next question is, I am planning to use induction heating in place to heat up a gas line. Someone has told me that I have to bridge the beginning and end of the pipe that I want to heat up. Is that true, and why?
So they are trying to create a loop. Induction heating likes to heat loops of any shape. So if you're trying to heat up a gas line, and depending on the length of your line that you're trying to heat, the loop may offer a better efficient setup to heat the metal tube, as the bridge that goes from the front to the back might create a loop. So again, if you are interested, we would love to look at some details to be able to then explain exactly what's happening in this situation.
All right, and we're going to wrap up pretty soon, but we'll just do another question or two here. Here's one that asks, I'm using an induction coil to heat a 3D printed Inconel mesh encapsulated in a tube to evaporate a liquid that passes through the heat exchanger. However, the coil is not asymmetrical. Would it be better, or would a better coil shape help to get a more homogeneous temperature over the length of the 10 centimeter long tube?
So you will need to know what kind of homogeneity is available through the 3D printed metal. If the 3D printed metal is somewhat homogeneous, then coil design can incorporate a uniformity of heat as is produced in the setup. If the 3D printed material is anisotropic, which means that the conduction paths are changing as you go along the length, then you may have to look at a different coil shape uh, by characterizing that individual uh, filter device that you're using. Thank you.
All right, and the next question is, while using an inert gas to prevent oxidation, how about the oxygen present in the quenching water?
So if the metal part never sees air and it's able to quench the metal part quickly inside the water, I suspect that you should not see much oxidation on the part. It is usually the transfer between the uh, inert environment and the water environment that you get that oxidation. However, if the inert cover is over the water, you may not get that oxidation. I don't have personal experience with it. If it is still a problem, you could use an oil to do your quenching, which should eliminate all the oxygen in the area. Thank you. Depending on the size and shape of the inductor, a simple soap solution might be all that is required. It's just like cleaning your copper utensils or stuff. So just normal cleaning agents would be okay. If it's a lot of buildup, you may have to resort to some industrial cleaning uh, fluids to clean those surfaces. So the question is that the uh, whether the temperature profile can be controlled during a heating cycle. Yes, there are some temperature measuring devices that are available that are able to be programmed to multiples of different steps in the heating cycle, so that once your temperature is reached, then it triggers a next step in the heating setup. So that is readily available and it can be provided easily.
All right, thank you, Girish. And while we do have a few more questions out there, I think Girish has answered over 40 questions at this point. So we'll give him a break and reach out to folks that we were unable to get to their questions after the webinar. So thank you so much for joining us today. We hope you found the webinar informative, and we'd appreciate your feedback. A brief survey will open when you leave the webinar. And be on the lookout for future webinars. In fact, there's a coil design webinar a week from today, and it's also free. We'd love to see you there. And as always, please let us know if there's any way in which we can help. Thanks again, and have a great remainder of your day.